Good morning, and let's continue with the discussion in module 3. So in the last class, we looked at the load line analysis of how to obtain the output voltage for a given input voltage by freeing the constraint variable. Vout was made a free variable, and then we plotted the current for the NMOS, PMOS transistors on the same axis, and then found the intersection where IDSN is equal to minus IDSP. Right? Then of course the conditions VGSN equal to Vin, VGSP is Vin minus VDD and so on have to be applied in order to find out various things. So the conclusion was this, that you take for Vin equal to 0, the NMOS current is essentially 0 along the x-axis. PMOS current, after mirroring about the x-axis and moving to the right, you will get a curve like this, which is the dotted blue line. Okay, yesterday I showed both of them in solid lines, but this one is slightly better because it differentiates PMOS currents with a dotted line, right? So the point of intersection is this big blue dot, okay, and therefore the output has to be VDD. Vout equal to VDD when Vin equal to 0. That's the only point of intersection that is possible, okay. I also pointed out that there are many other points of intersection with the other curves, like the blue dotted line intersects the magenta line, green line, light blue and red line, but those intersections have no meaning because they are actually for different Vins, and therefore don't get put off or confused by those points of intersection. You have to consider only the curves for the same Vin, and that point of intersection will be your final output, okay. So basically when I now move my Vin slightly above VTN, right, 0.4 VDD for example, I am assuming that is above VTN, then the magenta point of intersection will tell me very clearly that the NMOS is in saturation region because the solid line is clearly intersecting in the saturation region with the PMOS which is in the linear region, right. The green one of course is both of them are in saturation, somewhere in between it happens. Then the NMOS comes to linear, PMOS is in saturation, the blue dotted line is in saturation. Finally PMOS is, what's going to happen is if Vin is going to be VDD, then the NMOS will be turned on in linear region, PMOS will be cut off, right, and therefore the point of intersection is this red dot which is Vin equal to VDD, Vout equal to 0, okay. So as I told you, if there is leakage current, then this exact 0 and VDD will not happen. There has to be some current through the NMOS transistor, so the PMOS will adjust the VDS so that that amount of current is allowed through the NMOS transistor when Vin equal to 0, right. So then it will be slightly above 0, but it will be negligibly above 0, okay. So then we started discussing this switching threshold or the trip point, right. We were doing this analysis, and then after the class I realized that some of them were not very convinced with the argument I gave for why you should take the negative route, okay, when we considered the case of long channel devices. So what I'll do is, just for the benefit of doubt, I will go through the long channel derivation once more because that was done towards the end and maybe it was done in a slight hurry, okay. So let's just consider a long channel device, VDD, Vin, Vout, and this is a long channel. Okay, the width of the PMOS is WP, length is L, WN and length is L. Of course, length is always going to be 2 lambda. Width can be something else, okay. So now how do you find the switching threshold or the trip point? You basically plot Vin versus Vout. And then this is the VTC, right? Vout versus Vin. and then you plot V in equal to V out curve here. This point of intersection is, so this is V in equal to V out, right? Or maybe I should call it, yeah, because its y axis is V out equal to V in. Therefore, this point of intersection is Vm comma Pm. We want to find this point, right? And therefore, we are obviously these two devices now are in saturation region because the Vm is somewhere close to VDD by 2. Both devices are in saturation, right? Okay, this is only an assumption, by the way. It needs to be verified after you get the answers with numerical values to be sure that the assumption is correct. Okay, let me reiterate that point. So now what is our various things, right? VGS, VDS for NMOS and PMOS. V in equal to V out. So this is also equal to Vm. This is also equal to Vm. So what is VGS for the NMOS transistor? Vm. VDS? VDS is what? No, V naught, but here in this case V naught equal to V in equal to Vm. This also is Vm. For the PMOS, Vm minus, and this one, okay. So now IDSN for a long channel device is half of Kn prime Wp by L, sorry Wn by L, I am sorry, into Vm minus Vtn the whole square. IDSP is half of Kp prime Wp by L into Vm minus Vdd minus Vtp the whole square. Okay, on this curve, can you tell me this guy somewhere here is where Vtn is, somewhere here is Vdd plus Vtp, right? Or if you want me to be very careful and indicate that it's a negative value, I will say Vdd minus mod Vtp, just to show that it's a negative number there. Okay, so Vm is between these two values. Okay, Vm is necessarily greater than Vtn, otherwise the NMOS will not turn on, right? And it is also less than Vdd plus Vtp. Okay, this is the key point to note here, which means Vm minus Vtn is a positive number, but Vm minus Vdd minus Vtp is a negative number. Okay, this is the main thing. So this implies Vm minus Vtn is greater than 0, Vm minus Vdd minus Vtp is less than 0. Clear? Because this is the key data, that point that we need to find out the sign after we take the square root. Okay, so now what do? We go ahead and equate the two currents. Minus IDSP, right, implies Kn prime Wn into Vm minus Vtn the whole squared equals minus Kp prime Wp into Vdd minus Vtn, Vdd minus, no, Vm minus Vdd minus VTP whole square. Yesterday I defined that I don't know what I defined as R in this case, but let me now define Kp prime Wp, right, by Kn prime Wn itself as R. Kp prime is a negative number, so this is actually equal to mod of Kp prime Wp by Kn prime Wn. So it's a positive number. Okay. So therefore I can say Vm minus Vtn whole squared is R times Vm minus Vdd minus Vtp whole square. Now I am going to go ahead and take the square root. So Vm minus Vtn equals plus or minus R into V root R into Vm minus Vdd minus Vtp. Now this is a positive number, this is a negative number. How can these two be equal? Only if you take the negative root. So what this is basically saying is square root of x square, the positive root is what? Mod x. What if x is a negative number? Right? So therefore it is square root of x square, the positive root is always plus, mod x, and that's what this is. Minus of that negative number is nothing but modulus of that number, right? That's what we are using here. Therefore Vm minus Vtn equals minus root R into Vm minus Vdd minus Vtp, implies Vm equals Vtn plus root R into Vdd plus Vtp by, okay, this R and the R that we used for velocity saturation is different. That also, as you sort of consumes the Vd sat parameter, okay.